Welcome to the Discrete Universe podcast. Today on the Deep Dive, we're tackling a pretty bold alternative to our standard picture of the universe, quantum geometry dynamics, or QGD.
That's right.
This framework, laid out in Quantum Geometry Dynamics, an axiomatic approach to physics, it proposes some really radical rethinking of space, time, gravity, a whole lot.
It certainly does.
So our mission today is really to dissect the specific predictions QGD makes and kind of explore the implications, especially for, a physics-savvy audience like you.
Exactly. We've got the foundational text, and the plan is to go beyond just describing it. We want to dig into what QGD is actually suggesting about the universe, things that might go beyond our current established theories.
Okay.
So maybe the place to start is that QGD, it aims to reproduce the successes of existing physics. Think relativity, quantum mechanics.
Right, the things we know work observationally?
Precisely. But, and this is the key bit, it posits fundamentally different reasons for why these phenomena occur. The underlying assumptions are just different.
Okay, so, we see the same result on the surface. Maybe the math works out similarly in some cases, but QGD is saying the why underneath is completely different, like looking under the hood and finding a totally different kind of engine.
That's a good analogy. The what we observe might match, but the why is a new story. And, as the source emphasizes, the ultimate judge is always the scientific method.
Testable predictions.
Testable predictions, that's the currency. While QGD aligns with many observations, its core assumptions, especially about reality at the very smallest scales, are quite radical.
Okay, so where does it offer a really distinct prediction, something different?
Well, one big one is the accelerated expansion of the universe.
The dark energy problem. Or maybe not problem.
Potentially. Instead of meeting this mysterious dark energy component that makes up most of the universe in the standard model, QGD might offer an explanation baked into its core structure.
How does it do that? Is it modifying gravity somehow?
It is. QGD predicts this threshold distance. They call it day, pronounced d lambda.
E lambda.
Right. And beyond this d lambda distance, gravity, according to QGD, stops being attractive and actually becomes repulsive.
Whoa. Repulsive gravity.
At very large cosmological scales, yes. And this built-in repulsion could naturally explain why the expansion is accelerating without needing to invent a separate dark energy field.
That's elegant, if it works. I suppose the challenge is getting that d lambda value and the strength of the repulsion to match observations exactly.
Absolutely. That's a key test. The framework needs to predict the observed rate based on its fundamental parameters. That's ongoing work, as far as I understand.
Okay. What about other gravitational cornerstones? Like the weak equivalence principle. Does QGD uphold that?
It claims to, yes. The source states that the weak equivalence principle, the idea that gravity accelerates all objects equally, regardless of mass or composition, can be derived directly from QGD's equations for gravity.
So it's not an assumption, it's a result.
It emerges naturally from their formulation, according to the text. And related to interactions, QGD also proposes a specific mechanism for how momentum gets transferred during collisions. It involves discrete exchanges of these fundamental particles they call preons plus, or interactions via something called a pionic field.
Preons. Okay, we'll need to unpack what those are later. But it's trying to provide mechanisms, not just descriptions.
Exactly. Derivations from first principles, that's the goal.
What about relativity? Time dilation, length contraction, the usual suspects. Does QD reproduce those?
It does predict the effects, yes. Things like clocks slowing down in strong gravity or at high speeds, but again, the explanation is different.
How so?
Instead of space-time itself warping or time dilating in the way Einstein described, QGD suggests that the intrinsic physical mechanisms of the clocks themselves are what slow down.
So if I'm on a fast spaceship, my clock slows, not because time itself is different for me, but because the actual gears or the atomic oscillations or whatever are physically running slower due to my motion relative to this underlying preonic structure.
That's the QGD interpretation, precisely. The math might look similar in many cases, leading to the same observational predictions as SR and GR for things like time dilation, but the why is fundamentally mechanical, not geometrical in the space-time sense.
Interesting. Does this different view of gravity handle things like gravitational lensing or the precession of Mercury's orbit?
Yes, it claims to explain both. It does this by positing that the fundamental gravitational interaction in gravity between preons acts instantaneously.
Instantaneously. Okay, that sounds problematic for standard physics. No speed of light limit.
For the fundamental interaction itself, no. But this instantaneous action, combined with how mass influences the structure of this discrete quantum geometrical space, allows QGD to derive effects like lensing and Mercury's precession. The results apparently match observations very closely without invoking curved spacetime in the GR sense.
And this instantaneous idea, does it apply to other things, like binary pulsars losing energy?
Yes, the orbital decay of binary systems is also explained within this instantaneous gravity framework. It avoids the time delay issues you might expect from a purely Newtonian perspective, and apparently gets results similar to GR.
But, okay, you mentioned GR. QGD seems to take issue with Einstein's equivalence principle more broadly, too, right? Not just the weak version.
There's a thought experiment proposed in the QGD literature that challenges the strong equivalence principle, the idea that gravitational acceleration is indistinguishable from inertial acceleration, like being pushed back in your seat in a speeding car.
How does it challenge it?
QGD suggests that these two types of acceleration would actually have measurably different effects on an object's mass, momentum, and energy within its framework. If true, that would violate the equivalence principle as understood in general relativity. That's a potential experimental test right there, though likely a very difficult one.
Definitely. Now, perhaps the biggest divergence seems to be around gravitational waves. LIGO and Virgo have detected these ripples.
Yeah.
What's QGD's take?
Yeah, this is a really sharp break from the standard model. QGD flat out precludes the existence of gravitational waves as space-time ripples predicted by general relativity.
So, what were LIGO and Virgo detecting then?
I
Especially events like GW178718 that had, like, counterparts.
QGD offers an alternative explanation. It suggests those signals might actually be electromagnetic in nature.
Electromagnetic. How?
The idea is that incredibly energetic events like merging neutron stars or black holes could cause a large-scale polarization of this fundamental preonic field that permeates space in their model. Think of it maybe loosely like how moving charges create a magnetic field.
So, not a wave of space-time, but a wave in this preonic field, and that wave is electromagnetic.
That's the proposal. The characteristics of these waves, intensity, frequency, would depend on the properties of the source, like mass, density, velocity, and importantly, the local density of this preonic field.
And could these preonic field waves mimic the signals we attributed to gravitational waves?
QGD argues yes, that the effect of these polarized preonic field disturbances on the detectors could be practically indistinguishable from the effects predicted for GR's gravitational waves. Distinguishing them would require finding a unique prediction where the two models differ significantly.
Okay, this preonic field idea seems central. It all comes back to QGD's most fundamental axiom, doesn't it? The idea that space itself is discrete.
Absolutely. That's the bedrock. QGD starts by saying space isn't continuous, it's fundamentally quantum geometrical.
We have what?
It's composed of discrete entities they call preons minus, or just preons. And these aren't points in space. In a sense, they are space.
Okay, my brain hurts a little. How do they form space?
They're dimensionalized by a fundamental repulsive force between them, which QGD calls n-gravity. And this n-gravity is instantaneous. Dimensions like length, area, volume, they aren't fundamental. They emerge from the relationships and the number of these preons.
So our familiar Euclidean geometry is just an approximation that works well at large scales.
Exactly. Below some fundamental scale, QGD predicts significant deviations. The shortest distance between 2 points, fundamentally, might not even be a straight line in the Euclidean sense. It's about the path through these discrete preon units.
Wow. Okay, if space is discrete like that, made of preons, what about matter?
Right. If space has the structure, matter has to fit in. QGD introduces the preon plus, or P plus, as the fundamental particle of matter.
So preon minus is space, preon plus is matter.
Essentially. And the preon plus is described as purely kinetic. It doesn't sit still. It moves by constantly leaping from one preon site to an adjacent one.
Leaping.
That's the term used. And a key rule is that a single preon site can only hold one preon plus at any given moment. This preonic leap represents the fundamental unit of displacement. And because there's a fundamental distance related to the spacing of preons and a fundamental time related to the leap, there's a resulting fundamental speed.
Let me guess. The speed of light.
That's what QGD proposes. C isn't just a cosmic speed limit. It's a direct consequence of the discrete structure of space and the way preons plus move through it.
So C emerges from the structure. What about other fundamental concepts?
Mass energy.
QGD redefines them. The fundamental energy of a single preon plus is given a value numerically equal to its momentum, which is also equal to its fundamental speed, c. Wait, EP equals c for a fundamental particle.
Numerically, yes. Then, the energy of a composite object, like an electron or a proton, is simply the total number of preons plus it contains, which is its mass, m, in QGD, times this fundamental energy, so EEMC, not EMC squared. Right. QGD explicitly uses EMC and argues against the physical equivalence implied by Einstein's EBOMC-Hers. They see mass as the count of fundamental particles and energy as the sum of their intrinsic energies. It's a different conceptual relationship.
In momentum, velocity.
Momentum of an object is the vector sum of the momenta of all its constituent preons plus j. Velocity, interestingly, is defined as momentum divided by mass, pm, and QGD considers this an intrinsic frame-independent property.
Frame-independent velocity. How does that work with relativity?
Well, QGD distinguishes this intrinsic velocity from the metric velocity we typically measure. It actually suggests that due to the discrete nature of space, measuring this true intrinsic velocity directly is theoretically impossible. What we measure is always an average or an approximation based on traversing the discrete grid.
Okay, that's a lot to chew on. How does everyday gravity, the attraction we feel, arise from these leaping preons, plus in a sea of preons?
Good question. In QGD, gravity isn't about exchanging particles like gravitons, nor is it about space-time curvature. It arises from changes in the direction of the momentum vectors of the preons plus within interacting objects.
So the preons plus in my body and the preons plus in the Earth are subtly changing their directions of leaping because of each other's presence.
That's the gist of it. Importantly, this interaction doesn't involve a direct transfer of momentum or a change in the fundamental energy or mass count of the preons plus themselves, according to the model. It's purely a directional change.
And this mechanism leads back to the weak equivalence principle and that repulsive gravity beyond damned.
Yes, those are claimed to be consequences of this fundamental gravitational interaction mechanism. The repulsive component emerging at large distances is what could drive cosmic acceleration.
Let's shift to the bigger picture then. Cosmology. If QDD starts with this sea of preons, what's the universe's origin story? No Big Bang.
It's different. QGD proposes the initial state was simply a uniform distribution of free preons plus within the already existing quantum geometrical space, the preons. Sort of a smooth soup.
And the cosmic microwave background.
QGD suggests the observed isotropy of the CMBR arises naturally from this highly uniform initial state. No inflation required in the same sense as standard cosmology.
What about dark matter then? If it's not some exotic particle.
QGD proposes a simple candidate. Dark matter is just these free preons plus particles of matter that haven't clumped into atoms and stars.
So dark matter is just fundamental matter that's spread out.
That's the idea. And cosmological redshift, the stretching of light from distant galaxies, isn't just the Doppler effect from expansion. QGD says there's also a significant component due to gravitational redshift caused by the gravitational acceleration predicted by its own gravity equations over vast distances.
Does QGD cosmology picture the universe as infinite, expanding?
No, it actually proposes a finite discrete space. Because the number of preons, which are space, is conserved, space itself has a finite extent. It has a center and an edge, conceptually. It's the material universe, the structures made of preons plus He, that expands within the static preon space driven by that repulsive gravity at large scales.
A finite, static space with an expanding material content, that's quite different. What about the ultra-dense regions? Black holes.
They get a QGD interpretation, too. Black holes are seen as structures with gravity so intense that they can break down all forms of matter, even photons, into their constituent preons plus A.
So matter falls in and gets dissolved into fundamental preons plus A.
Exactly. Which means any emission from such an object wouldn't be electromagnetic radiation as we normally think of it, like Hawking radiation, but would likely be emission of these preons plus themselves.
Which would be invisible to our telescopes.
Presumably, yes. QGD also predicts black holes are extremely dense, but crucially, not infinitely dense. The discrete nature of space imposes a limit.
No singularity. Does that help with the information loss paradox?
QGD argues that information loss is consistent with its axiom, so it doesn't lead to a paradox within its own framework. If matter is fundamentally just arrangements of preons plus rearranging or disassociating them, isn't inherently paradoxical.
Okay, one last big topic. Time. We touched on time dilation, but what is time fundamentally in QGD?
Time is treated as purely relational. It's a mathematical concept we use to track the sequence of events, the evolution of physical systems. It's not a fundamental dimension or substance in itself.
So the slowing clocks we talked about earlier.
That's just the clock's physical mechanism slowing down due to its state of motion or the gravitational environment, not time itself changing its flow. QGD provides derivations that reproduce the effects of time dilation from special relativity, but interprets them purely mechanically.
Does this view of time and space lead to any other testable predictions?
Yes, a potentially crucial one involves the speed of light. QGD predicts that while a two-way measurement of the speed of light, like bouncing radar off Venus, will always yield c, a one-way measurement should vary depending on the observer's own intrinsic velocity through the prion grid.
Ah, the old one-way versus two-way speed of light problem. Most experiments measure two-way. A definitive one-way measurement is notoriously tricky.
Extremely tricky. But QGD makes a specific prediction. The one-way speed should differ. If that could be measured and confirmed, it would be strong evidence for this kind of underlying structure and a blow to standard relativity's postulates.
So wrapping this up, the core idea is this fundamental discreteness of space, right? Prions making space, prions plus moving through it, and from that flows, well, pretty much everything else.
That's the heart of it. This discreteness ripples outwards, forcing reinterpretations of mass, energy, gravity, cosmology, even time. It suggests concepts we often take as fundamental continuity, infinity. Maybe time itself might be just mathematical tools or emergent properties, not the bedrock reality.
And what's really striking for anyone listening with a physics background is how QGD tries to build this whole alternative picture from just a few starting axioms.
Right. It's an attempt at a self-consistent axiomatic system. And the payoff, or the challenge, lies in those specific testable predictions where it diverges from the standard models.
Like the variable one-way speed of light you mentioned.
Exactly. Or the idea that those gravitational wave signals are actually electromagnetic effects in the prionic field. Those are points where future experiments could potentially distinguish between the theories.
And that repulsive gravity idea, governed by d lambda, offers a completely different take on cosmic expansion and how structures form on the largest scales.
It really does. It provides an internal mechanism rather than requiring an external add-on like dark energy.
So this deep dive into QGD, it really underscores how even our most successful models like GR and QM might have radically different explanations waiting underneath. And it brings home how vital those concrete, testable predictions are for actually figuring out which story is right.
Absolutely. It's a reminder that physics is always probing deeper, questioning assumptions.
It leaves us with a pretty provocative thought, doesn't it? If space is fundamentally discrete, and if gravity flips its sign at some vast scale, what other seemingly solid parts of our physical reality might just be, I don't know, emergent features of this deeper, granular, quantum geometrical universe?
That's the big question QGD opens up. We've really only scratched the surface today. There's clearly a lot more to explore and, crucially, to test.